Special relativity, also referred to as special theory of relativity in physics, is a commonly recognized and experimentally established physical theory about the connection between time and space. According to Albert Einstein's academic treatment, it is based on two hypotheses. The laws of physics are invariant, which is identical in all inertial. The speed of light in vacuum is same for all those who observe, irrespective of the motion of the source of light. The laws were initially suggested by Albert Einstein, that was published in 1905 in paper on the electrodynamics of moving bodies. The discrepancy of Maxwell's equations of electromagnetism with Newtonian mechanics and the absence of investigational validation for a theorized luminiferous ether is what caused the progress of special relativity. That amends mechanics to take care of situations which involve motions which is nearing the speed of light. Today, special relativity is a precise model of motion at any given speed. Even if the model of Newtonian's mechanics continues to be useful, as it is precise and simple, approximately at minor velocities relative to the speed of light. Special relativity suggests a broad range of magnitudes which have been experimentally proved, including time dilation, length contraction, relativity of simultaneity, universal speed limit, and mass-energy equivalence. It has taken the place of conservative belief of a complete universal time with the idea of a time which depends on reference frame and spatial position. Instead of an invariant time gap between two events, there is an invariant space-time interval. If combined with other laws of physics, there are two assumptions of special relativity, which foretell the equivalence of energy and mass, which is conveyed in the energy-mass equivalence formula, E is equals to mc squared, c being the speed of light in vacuum. An important aspect of special relativity is that the Galilean transformations of Newtonian mechanics have taken the place of Lorentz transformations. There cannot be a definition for space and time if they are separated from each other. In fact, space and time are intertwined in a single continuum, which is referred to as a space-time. Events which occur at the same time for a particular observer may happen at different times for a different observer. This is a special theory and implies especially when the curvature of space-time is negligible because of gravity. Albert Einstein framed general relativity in 1915. Disagreeing certain outdated descriptions, special relativity has the ability of managing accelerated frames of references. Today, Galilean relativity is reflected, an estimate of special relativity which is effective for low speeds. Special relativity is reflected as estimate of general relativity, which is effective for gravitational fields in conditions of free fall and a very small scale. While general relativity includes non-Euclidean geometry, so as to characterize the gravitational effects as the geometric curvature of space-time, special relativity is contained to the flat space-time referred to as Minkowski space. A closed by Lorentz invariant frame which stands by special relativity can be described at small gauges even in curved space-time. Earlier, Galileo Galilei has already hypothesized that there is no definite and complete state of rest through a principle which is known as Galileo's principle of relativity. Albert Einstein stretched this principle so that it took into account the speed of light, an occurrence that had been recently uncovered in the Michelson-Morley experiment. He also hypothesized that it is applicable for all the laws of physics, inclusive the two laws of electrodynamics and mechanics. Although the fundamentals of physics might not be quite understood by everyone, but it is something which is unknowingly used in our daily life. No matter how hard the subject may be to learn, but it helps us make our lives easy. It plays an important role in the history of mankind and will continue to hold a pivotal place in futuristic science and technology. For those who admire the subject, physics can be an intellectual experience and when studied deeper will never stop to amaze. It is the most basic amongst all the sciences, and other sciences like chemistry, biology, geology, or cosmology can be understood by the theories which have been developed in physics. Most of the tools on which the progress of technology and science are dependent have been produced by physics. The presence of physics can be felt all around you, from checking your blood pressure to getting an X-ray done, from petrol required to run your vehicle to electricity at your home, from an email that you sent from your computer or laptop to a smartphone that you love to flash, from an airplane to a ship, from a DVD to a television, and even the house that you live in is built with the help of physics. A country's development highly depends on how strong the nation's team of physics researchers or institutes are. Nations understand the importance of physics, and which is why they encourage researches which in turn help in overall development of the country. Understanding physics is important and easy.